Welcome back. In today's video, we're going to explore the design of a Retrieval-Augmented Generation system, often called RAG. At a high level, RAG combines two powerful ideas: retrieval, where we search a knowledge base to find the most relevant information, and generation, where a large language model takes that retrieved information and produces a fluent, grounded answer. A practical example is ChatPDF. Imagine a company uploads its HR policies, technical manuals, or training guides. Employees can then ask natural language questions like, "How many vacation days do I have?" or "What's the process for requesting new equipment?" Instead of memorizing the whole manual or retraining the model, the system retrieves the relevant sections from the company documents and uses the language model to generate a clear answer. In this session, we'll cover the requirements we need to clarify, how to frame the problem as an ML task, the steps for preparing and indexing data, and finally, how to design the RAG system pipeline itself. By the end, you'll see how RAG provides a scalable, efficient, and up-to-date solution for question answering over dynamic knowledge bases, a critical capability for modern enterprise AI applications. The problem is to design a RAG system, or a chatbot, that answers employee questions using internal company documents. What does the external knowledge base consist of? Does it change over time? Does the data contain text, images, and videos? Does the data follow a fixed format or template? Should the system respond in real time? How much data do we have in total? Designing a ChatPDF-like system fundamentally revolves around transforming a user's text prompt into an accurate and relevant text response that addresses the query based on PDF content. This is essentially a natural language understanding and generation task tailored to specific document data. There are three primary approaches to achieve this. 1. Fine-tuning. Start with a pre-trained general-purpose large language model, LLM, and fine-tune it on company-specific or domain-specific data extracted from the PDFs. This approach enables high customizability and enhanced accuracy tailored to the company's documents. However, fine-tuning is computationally expensive, requires frequent retraining as data changes, demands significant technical expertise, and needs an extensive data set to avoid overfitting or loss of general language understanding. 2nd, prompt engineering. Instead of retraining, carefully craft input prompts that include relevant company data to guide the pre-trained LLM's output. This method offers ease of use, cost-effectiveness, and flexibility to quickly update prompts as needed. On the downside, prompt engineering can lead to inconsistent outputs and is limited by the LLM's existing knowledge, which may not fully cover the company's specific content. 3. Retrieval-Augmented Generation, RAG. This hybrid method combines a retrieval system that fetches relevant information from external sources or company documents with a generative LLM that produces the response based on retrieved context. RAG provides access to up-to-date information and improves contextual relevance of answers. However, implementing RAG introduces complexity in building and maintaining the retrieval infrastructure and heavily depends on the quality of retrieval results to ensure accurate generation. In summary, framing this problem as an ML task requires balancing accuracy, cost, flexibility, and complexity depending on business needs and available resources. Understanding these trade-offs is key to selecting the right architecture for a ChatPDF-like system. Data preparation is a critical stage in building a ChatPDF-like system, as it transforms raw PDF content into a format that a language model can effectively utilize for query answering. The process consists of 3 main steps: document parsing, chunking, and indexing. 1. Document parsing. The first step involves extracting text, images, tables, and other elements from PDFs and converting them into a structured, machine-readable format. This can be done using rule-based parsers, which rely on predefined rules to identify and extract content, or AI-based parsers that use techniques like object detection and optical character recognition to interpret more complex layouts and scanned images. AI-based parsing is more flexible but can require more resources and fine-tuning. 2. Document chunking. After parsing, the text is often very long and unstructured, so it is divided into smaller, manageable chunks that the model can process efficiently. Chunking methods include length-based chunking, splitting text into fixed-size segments, regular expression-based chunking for semantic boundaries, and specialized splitters for formats like HTML, Markdown, or code. Effective chunking balances chunk size and semantic completeness to retain meaningful context for retrieval and generation. 3. Indexing. The chunked data is then organized into an index to enable fast and relevant information retrieval during inference. There are several approaches. Keyword-based retrieval matches exact query terms. Full-text search scans entire documents for matches, but can be inefficient. Graph-based retrieval leverages relationships between entities to retrieve contextually connected information. Vector-based retrieval converts chunks into high-dimensional embeddings that capture semantic meaning, allowing similarity searches beyond exact text matches. Vector-based retrieval is the preferred choice here due to its advantages in semantic understanding, scalability, and efficiency, making it well-suited for handling large document corpora with nuanced queries. This data preparation pipeline lays the groundwork for precise, context-aware responses by the language model. In the model architecture for a chat PDF-like system, the focus is on enabling efficient and semantically meaningful retrieval and generation by working with vector embeddings. Indexing. The key task is to convert the chunked data into dense vector representations or embeddings that capture semantic meaning beyond just the raw text. For text data, we use a text encoder, typically an encoder-only transformer model. This neural network processes input text chunks and produces fixed-length embeddings that represent the content's meaning in a continuous vector space. For image data extracted from PDFs, an image encoder, often transformer-based, is used to convert images into embeddings. Crucially, the system aligns image and text embeddings into a shared embedding space. This alignment enables multimodal retrieval and improves the system's understanding by linking visual and textual information, similar to how image captioning models learn to associate images with descriptive text. Retrieval. At inference time, user queries are encoded into the same embedding space using the text encoder, allowing the system to find the most semantically relevant chunks by measuring vector similarity. This semantic retrieval is far more flexible and accurate than keyword matching, especially for nuanced queries. Generation. After retrieval, the generation component takes both the user query and the retrieved relevant content chunks to produce a final, context-aware response. This step typically involves a large language model that synthesizes information and generates coherent, precise answers tailored to the query. Together, these components ensure the system can effectively understand diverse inputs, retrieve contextually relevant knowledge, and generate accurate responses grounded in the document content. When designing a chat PDF-like system using Retrieval-Augmented Generation RAG, it's important to understand that most components begin with pre-trained models. Fine-tuning the large language model, LLM, is typically not the immediate step to optimize performance. Why? Pre-trained models already have strong general language understanding and generation capabilities. The retrieval component plays a crucial role in providing relevant context to the LLM. Fine-tuning should be considered mainly if the system consistently fails to produce accurate or contextually relevant answers. This approach avoids unnecessary computational cost and complexity. Retrieval-Augmented Fine-Tuning, RAFT, is a specialized fine-tuning technique designed to improve performance by teaching the model to distinguish between relevant and irrelevant documents retrieved during inference. Key components of RAFT include document labeling. Each retrieved document is labeled as either relevant, golden, or irrelevant distractor, based on its usefulness for generating correct responses. This labeling is critical for supervised fine-tuning. Joint training. The model is trained to generate responses using relevant documents while minimizing the influence of irrelevant ones. This is achieved by modifying the loss function to penalize the model if it relies on irrelevant information during generation. By incorporating RAFT, the system learns to better leverage high-quality context and avoid distractions, which enhances the accuracy and reliability of generated answers. This fine-tuning step can significantly boost performance, especially in complex or noisy document environments. The sampling phase in a chat PDF-like system is crucial to generating accurate, coherent, and contextually relevant responses based on the user query and retrieved information. Retrieval. First, the system encodes the user's query into a dense vector representation, or query embedding. Then, a nearest neighbor search is performed to find the most relevant chunks from the index document embeddings. This search can be executed using different algorithms such as Tree-based methods, which organize data hierarchically for efficient search. Locality-sensitive hashing, LSH, which hashes similar items into the same buckets to speed up similarity queries. Clustering-based approaches that group data and narrow down search to relevant clusters. Graph-based methods that navigate connections between data points for retrieval. Generation, the retrieved context along with the original query is fed into the generative model to produce the final response. Top P sampling, nucleus sampling, is used during generation to dynamically select from the most probable tokens while maintaining output diversity and quality. Enhancing generation with prompt engineering. Several prompting techniques can further improve the quality and relevance of the generated responses. Chain of thought prompting guides the model through intermediate reasoning steps before giving the final answer, which helps with complex queries. Few-shot prompting provides the model with a few example input-output pairs to shape its responses. Role-specific prompting instructs the model to adopt a particular persona or role to tailor the tone and style. User context prompting incorporates user-specific information into the prompt to personalize the response. Together, these techniques ensure that the system not only retrieves relevant information efficiently, but also generates well-structured and user-tailored responses. Evaluating a chat-PDF-like system involves multiple facets to ensure both the retrieval and generation components are delivering accurate, relevant, and trustworthy responses. Context relevance. This measures how well the retrieval component selects the most pertinent documents or chunks in response to the user query. Key metrics include hit rate, the percentage of queries for which at least one relevant document is retrieved. Mean reciprocal rank, MRR, evaluates the rank position of the first relevant document. Higher scores indicate relevant documents appear earlier in the list. Normalized discounted cumulative gain, NDCG, considers the position of relevant documents in the ranked list, giving more weight to documents appearing earlier. Precision at K, the proportion of relevant documents among the top K retrieved items. Faithfulness. This assesses whether the generated response accurately reflects the retrieved context without introducing incorrect or hallucinated information. Faithfulness is often evaluated through human evaluation, where experts judge factual consistency, automated fact-checking tools that cross-verify facts against trusted knowledge bases, consistency checks that ensure the answer doesn't contradict retrieved documents. Answer relevance focuses on how well the final answer addresses the user's query in terms of completeness and conciseness, avoiding redundant information. Answer correctness measures the alignment between the generated answer and a known correct reference, evaluating accuracy. Together, these evaluation dimensions help maintain a system that is not only responsive but also reliable and informative, ensuring a quality user experience. Let's walk through the overall system design for a chat PDF-like application, highlighting the key components that enable efficient, safe, and accurate document-based question answering. Indexing process. The system begins by converting the entire knowledge base, including text and images, into dense vector embeddings. These embeddings capture semantic meaning, allowing for similarity comparisons beyond simple keyword matching. The embeddings are stored in an index table optimized for fast retrieval, often using specialized data structures suited for nearest neighbor search. Safety filtering. Before processing user queries, the system applies a safety filter to ensure that the input is appropriate and complies with usage guidelines. This protects the system from harmful or malicious requests, maintaining a trustworthy user experience. Query expansion. To improve retrieval accuracy, the system performs query expansion, where the user's initial query is enriched or broadened. This helps the retrieval component find relevant documents even if the original query is ambiguous or incomplete, enhancing overall system responsiveness. Retrieval. Using an approximate nearest neighbor (ANN) algorithm, the system searches the indexed embeddings to find the data chunks most semantically relevant to the expanded query. This step narrows down vast document collections to a manageable set of candidates. Generation. Finally, the generation component synthesizes a coherent and context-aware response by combining the original user query with the retrieved information. This step leverages a large language model to produce precise and user-friendly answers. Together, these components create a seamless pipeline that transforms raw documents into actionable knowledge, enabling users to interact naturally and effectively with large, complex data sets.